So welcome back everyone. This is Ravindra Thube, faculty at BYJU'S Exam Prep, India's largest learning platform. So welcome back everybody. We were discussing about electrochemical machining operation yesterday. So just quickly we'll recap, everybody joining, right, fine. And today is the session where we'll try to discuss the numerical part of electrochemical machining operation. That's the most important thing as far as GATE examination point of view is concerned. Is it true everybody? So please join, let the others also do join this, right, fine, everyone. So we are just about to start the session. Everyone. Is it okay everybody? We are just about to start the session. Okay, fine. So we'll quickly recap what exactly we were discussing yesterday. So we were discussing electrochemical machining operation, and when we say electrochemical machining operation, it stands for what? A non-traditional machining operation. So what is the basic principle of removal of material? It states that whenever two conducting electrodes are immersed in a conducting electrolytic solution, then whichever the electrode is connected to positively charged terminal, it will start depleting the ions. And these positively charged ions will get attracted to negatively charged terminal, that is cathode, and it will get deposited. So this principle is utilized in electroplating or electrocoating. So whenever we want to generate one new layer of the material on some workpiece, we perform this electroplating or electrocoating. But right now in electrochemical machining operation, we don't want to deposit the material, we want to remove the material from the workpiece. And therefore we do one thing, that we change the polarities of the workpiece and the electrode. So here in the electroplating, my workpiece is connected to negatively charged, but in electrochemical machining operation, my workpiece is connected to the positive charge terminal and it is acting as a anode. It is acting as what? Anode. Absolutely true. So now the same principle. So whenever we are connecting this particular both terminals to the power supply, and when they are immersed in a conducting electrolytic solution, then the positively charged terminal will start depleting ions. And whenever the ions are depleting, that is the principle of removal of material, which is nothing but called as ion depleting or ion dissolution. Is it true? Yes. So yesterday we discussed one particular example. We have discussed that, sir, this is my workpiece which is connected to positively charged terminal and it is acting as an anode, and this is my tool which is connected to negatively charged terminal. It is acting as a cathode. It is acting as what? Cathode. So there is one conducting electrolytic solution we have selected, which is a sodium chloride with water, which is nothing but called as a salt solution. Right? This is what exactly good conductor of electricity. And whenever the power supply is given, there is a potential created between the workpiece and the tool. And we know that there is a gap is maintained. They are not connected to each other. Are they? No. There is a gap. And that gap is filled with a conducting electrolytic solution. And we know that because of the potential created there, the NaCl will get decomposed, or ionization of this will take place. Na plus and Cl minus ions will be generated. So if you can say that here in this gap, there will be so many Na plus and Cl minus ions should be there. And now the electrical circuit will be completed. And because as workpiece is connected to positively charged terminal, it will start depleting ions. And now as we are selected in this example, my workpiece is of ferrous material, so Fe will deplete a Fe++ ions and 2 electrons. And we have discussed yesterday that the atom has a structure, so 2 electrons are released, so it will have a positive charge, and that atom will release in the form of ions, that is Fe++ ions. Yesterday we had discussed up till now. So now we'll discuss the next parameter. So now what happens, whatever water is present there, yesterday I told you that, right, water, now water comes in the picture here. So whatever the water is, H2O, that what exactly water is, that will also get separated into H plus ions and hydroxyl ions, OH minus. What is that? H plus ions and hydroxyl ions. Now what happens, whatever the gap is present, right, whatever the gap is present between tool and the workpiece, in that gap what is present? Na plus and Cl minus ions are present, H plus and OH minus ions are present, and Fe++ ions with 2 electrons are present in this particular gap. And we all know that whenever the ions are depleting, can I say that these are positively charged ions, therefore these ions getting quickly attracted to the negatively charged terminal cathode, which is tool. Because they are not apart from each other, that the tool and the workpiece are not apart from each other miles away. They are very close to each other. We know that they are not in contact. There is a certain gap, but you can understand that. So what happens, whichever the ions are depleting, these ions will quickly get attracted towards tool. And whenever these ions are getting attracted, they'll get deposited to the tool material, because we know that opposite attracts to each other. That's what happen in the real life. The same thing is happen. The positively charged ions will get attracted to the tool and they get deposited. And therefore, one more new layer will be generated. But sir, we understand here we are not interested in terms of any kind of deposition or electrocoating in tool or workpiece. I want my tool shape to remain as it is throughout machining operation. Why do I want that whatever the ions are depleting, that should get deposited on the tool? So ions are depleting, I am very happy till now, okay, because we want that material should remove in the form of ions. I'm extremely happy, but I want that ion should not get deposited on the tool. And that is what the reason, whatever this conducting electrolytic solution is selected as a salt water. Now what happens when the ions are depleted, before they get deposited onto tool material, can I say that these Fe++ ions, these what? Fe++ ions will get reacted to the chlorine, because chlorine ions, Cl- ions are also in between them, and therefore what happens here, let's listen. These Fe++ ions are getting reacted with a Cl- ions, and it will generate a ferrous chloride as a precipitate. There is a precipitate formation takes place. What will generate? FeCl2. It is nothing but called as ferrous chloride, and it is nothing but a precipitate. In the chemistry lab, you must have heard about precipitation. It is a non-reactive chemical, I would say, that material, and that precipitate can be collected at the bottom of the chamber. And therefore, here you can say that FeCl2, it is ferrous chloride. That is what? Precipitate generated. In the same manner, Fe++ will get reacted, Fe++ will get reacted to the hydroxyl ion, that is OH minus. How many hydroxyl ions? 2 hydroxyl ions it will get reacted to, and it will generate a ferrous hydroxide. It is FeOH twice, FeOH twice. This is exactly equal to one more precipitation. So I can write down here FeOH twice. That is what exactly a precipitate formation takes place here, ferrous hydroxide. So which means that whatever the ions are liberated from the workpiece material, these ions are not allowed to deposit it onto tool material, and in between that there are artificially certain chemical reactions are generated in such a way that ferrous or Fe++ ions should chemically react with chlorine ions and the hydroxyl ions to manufacture ferrous chloride and ferrous hydroxide as a precipitate formation, which can be collected at the bottom of this particular chamber. And therefore both things are satisfied here. There is no deposition of any metal on the tool, so tool will remain as it is, and therefore, and whatever the ions are depleting from the workpiece material, it is nothing but called as my material removal. So both things happening. From the workpiece, material removal takes place. On the tool material, there is no deposition, and simultaneously whatever these H+ ions are there, right? H+ ions are there. These H+ ions are getting reacted. I'll write down here. These H+ ions, 2 H+ ions are getting reacted with the 2 electrons. H+ ions are getting reacted with what? 2 electron, and it will generate a hydrogen gas. It will generate what? Hydrogen gas. And this hydrogen gas can be liberated to the atmosphere. This hydrogen gas can be what? Liberated to atmosphere. So this is exactly H2 gas is released to the atmosphere. Is it understood, everybody? Yes. And there might be a chances that one more reaction can take place here, that is Na+, right, can react, Na+ can react to hydroxyl ions, and it can just manufacture sodium hydroxide. What it can generate? It can generate NaOH, sodium hydroxide. This is also one kind of precipitate formation can be generated, right? So these are nothing but typical chemical reactions happening. But point to be understand here, now what ion dissolution is the mechanism by which material removal takes place from the workpiece. Is it understood, everybody? Yes. I hope so. Is it correct? Right. Fine. So now let's say that I'll just write down here what is exactly equal to mechanism of material removal. It is nothing but ion dissolution. Ion dissolution, or it can be also called as a ion deplating. Ion deplating. So this is what exactly ion dissolution or ion deplating. This is what exactly mechanism of removal of material. Right, fine. Now next question I have to ask you that what exactly is the typical workpiece material for this particular process is developed. So it's very simple that the mechanism of removal of material is ion deplating or ion dissolution. And therefore we can easily say that, sir, whatever the mechanical properties of the workpiece is, whether the material is hard, brittle, malleable, ductile, it has no impact as far as material removal is concerned. So therefore, any workpiece material, whether it is a hard or a brittle or malleable or ductile, all the kind of materials can get machined in the electrochemical machining operation. There is no restriction. Because if we go and talk about ultrasonic machining operation, in the ultrasonic machining operation, the mechanism of removal of material is the impact load is created by this abrasive particle and the brittle fracture leads to removal of material. So there only brittle materials can get machined, ductile materials cannot get machined in a ultrasonic machining operation. But right now, whether the mechanical properties has no impact on the material removal, because whether the material is malleable or ductile or anything, but material removal process has a principle of ion deplating, so there is no particular impact of the mechanical properties of workpiece on a MRR. And therefore, I'll say that, sir, material removal rate is independent of mechanical properties of the workpiece. Most of the workpieces can get machined in electrochemical machining operation. We don't have any problem, provided that the workpiece should be electrically conductor. If the workpiece is not electrical conductor, there will be no circuit completed, and if the electrical circuit is not completed, the ions will not get depleted. So therefore, the workpiece should have electrical conductivity property. If the workpiece is not a conductor of electricity, there won't be any kind of machining operation would take place. So therefore, most of the materials or the workpieces which are conductor of electricity can get machined. Right, fine. Next question. What is the ideal properties of the tool material? So we also know that, so tool also technically speaking should be conductor of electricity. If there is a resistance created to the flow of current, then it will be a loss of energy into the system itself. And whenever the resistance is created to the flow of current, can I say a lot of energy might release in terms of heat and temperature of the tool might increase. And therefore, it's very simple that I would say that the tool material should be also selected in such a manner that it should support my machining operation. So therefore, any good conductor of electricity material should be selected as a tool material. So can I say copper and aluminum are conductor of electricity? Generally copper metal is selected, right? As far as ideal tool, as far as electrochemical machining operation is concerned. Now you tell me, what is the medium of machining operation? So what is the medium in which we have performed operation? Sir, whatever the medium is present between tool and the workpiece, that medium has to be electrical conductor. Then only my electrical circuit will completed, and then only ions will get depleted. If there is no electrical conductor medium is present, so no particular ion depletion will take place, which means that the requirement of the system is my material present there should be what? Should be conductor of electricity. And if it should be a conductor of electricity, that means my medium required is conductor of electricity. Conducting electrolytic solution is required. What is required? Conducting electrolytic solution. Fine. Next question. Then what is wear ratio or machining ratio? So we know that, we have already discussed that. What is wear ratio? So wear ratio or machining ratio is nothing but material removal takes place on workpiece. What is the volume of material removal takes place on the workpiece divided by what? Wear of a tool. What is that? Sometimes it is called as tool wear of a tool. This ratio is nothing but called as wear ratio or machining ratio. Now you tell me that what is the wear takes place on this tool material? Is there any chemical reaction takes place on the tool? No. Hydrogen gas is released, that's it. There is no chemical reaction. Is there any material deposited onto tool material? No. There is no deposition takes place, which means that there is no chemical reaction takes place on the tool material. There is no reaction. There is no deposition. That means tool will remain as it is. Wear of the tool is what? 0. So I'll say that, sir, wear of the tool is 0. That means wear ratio will be infinity. That means, can I say same tool can be utilized infinite number of time, technically speaking, for manufacturing different number of components. So wear ratio is infinite. So one by one, we'll just revise what are exactly the discussion would be. Right, fine. So we can easily say that, sir, mechanism of removal of material is ion dissolution or ion depleting. Workpiece material should be just electrical conductor. There is no restriction, right, beyond that. Tool material. What would be tool material? Any conducting metal rod can be considered as a tool material, but it should be a good conductor of electricity. Right, fine. Medium of machining operation. A requirement of medium of machining operation is conducting electrolytic solution has to be there. If there is no conductivity, then electrical circuit will not completed, electromotive force will not be generated, and the ions will not get depleted from the workpiece. That is what mechanism of removal of material. And last but not least, wear ratio or machining ratio has to be infinite because my tool wear is literally 0. There is no reaction. There are no reaction taken place on that particular workpiece material. As there is no reaction take place on the workpiece material, I'll say that wear ratio is exactly equal to infinity. Right, fine. Now we'll discuss the influencing factors of MRI. And here the technical part as far as numerical point of view is concerned we are talking about. Now let's talk about what are the influencing factors. Now in the previous session we have discussed that what does mean by influencing factors. Whichever the factors who has an impact on material removal rate, these all the factors are nothing but influencing factors of my machining. In the conventional machining operation we have discussed that if I increase the depth of cut from 1 millimeter to 2 millimeter. So if I increase the depth of cut from 1 millimeter to 2 millimeter, can I say that my material removal rate will increase, volume of material which is removing is going to increase, and so many parameters is going to happen, which means that depth of cut has impact. In the same manner, you tell me that what are the influencing factors of MRR. So first factor is, so whenever Faraday has proved the law of electrolysis, there is a first statement was written, whenever two conducting metal electrodes are immersed in a conducting electrolytic solution, whichever the electrode is connected to the positively charged terminal, it will start depleting the ions. And the moment ions are depleting, that whatever ions are depleting is nothing but my removal of material from the workpiece. So which means that if more and more ions are depleting, can I say material removal rate will be more? If less number of ions are depleting, material removal rate will be less. It's a very simple statement, right? What is material removal rate mechanism? Ion depleting, ion dissolution. So from this workpiece, if more and more Fe++ ions are depleting, that means my material removal rate will be naturally more. So if I want to have more material removal rate, if I want to have MRR to be higher, so more ions to be get depleted. So which means that can I say that in a simple term, more ions are depleting, material removal rate is higher. Less ions are depleting, material removal rate will be less. So in the same manner, the Faraday has proved the next statement, the mass of substance deposited or retorted, mass of substance deposited or liberated at any electrode is directly proportional to amount of charge passed or amount of charge carried. Charge, अभी charge क्या होता है? Charge is nothing but one kind of. What is charge? Charge is nothing but simply current. So what is that? However the amount of current or charge is passed through that electrical circuit, then material removal rate or ion depleting are directly proportional to that charge. Sir, it's very simple that whenever there is a machining happening, that means some amount of energy is utilized for removal of that material. So what energy? The electrical energy is flowing. Then because of that electrical energy is flowing, there is an electromotive force is generated. That don't require to go into that much trouble and detail. It's very simple that ions are depleting and they are attracting towards tool. So there must have been somebody who must have been pulling that particular ions from this workpiece and attracting towards the tool. So that whatever is there which is pulling these ions is nothing but called as EMF. It is called as electromotive force. And as the electrical current flowing, if the density of the current is more and more, if the current is more and more, can I say electromotive force will be more, and therefore more and more ions will get depleted, and that current itself is nothing but called a charge. So more the current, more the charge, the more the ions will get depleted. If the more ions are depleting, my material removal rate will be higher. So which means that the material removal rate, or it is nothing but called as the mass of substance liberated at any electrode, from any electrode, is directly proportional to amount of charge carried. So which means that I'll say material removed. Material removed. From where? From the workpiece. Material removed is what? Directly proportional to amount of charge carried. Q is nothing but total charge carried. But sir, I am not interested to calculate material removed, total material removed. We are interested to calculate rate. And we know that rate is always calculated with respect to time. Because whenever I say that rate is calculated with respect to what? Time. So which means that, sir, you don't tell me that how much is the total amount of material removed. You tell me that how much amount of material removed in 1 minute or 1 second or 1 hour. That means we have to measure with respect to time. So therefore I am interested to calculate material removal rate is directly proportional to amount of charge carried. Q is total charge carried. Now I'll take it that how much amount of charge is carried with respect to time t. and this is nothing but called as MRR is directly proportional to amount of charge carried per second. Right? Fine. Is it understood, everybody? Yes. Q stands for what? Charge. Amount of charge carried per second. Now, if I ask you a definition of current, what is definition of current? The technical definition of current is nothing but amount of charge carried per second. That is what? Charge which is carrying. And who is carrying that charge? The charge is carried in the solid by electrons. By what? Electrons. So, amount of charge carried per second is nothing but called as what? Current. So, which means that in a technical term, we can directly write down here that material removal rate is directly proportional to I. And here I stands for my current density. It is called as what? A current density. And can I say that this current density is mentioned in what? Ampere. What is the unit? Ampere is the unit. Current density. Is it true? Yes. So I'll say that the first statement is that. Which one is the influencing factors of MRR? Influencing factors of MRR is nothing but the factors which are influencing material removal rate. So I'll say that, sir, MRR is directly proportional to the current I. MRR is directly proportional to I. Is it understood? Yes. Now in the same manner, there was third particular statement was written in related to the Faraday's first law of electrolysis, and which is nothing but the amount of substance deposited or liberated from any electrode is directly proportional to chemical equivalent weight, and that is sometimes also called as electrochemical equivalent. It is called as what? Electrochemical equivalent. That means material removal rate is directly proportional to small e, and the small e stands for what? Electrochemical equivalent. Electrochemical equivalent of substance. Electrochemical equivalent. Is it true? Yes. And what is the definition of electrochemical equivalent? Electrochemical equivalent is nothing but gram atomic weight divided by valency. So A stands for here gram atomic weight divided by Z. I'm just utilizing these letters. Z, it is nothing but stands for a valency. So which means that material removal rate is directly proportional to electrochemical equivalent. It is sometimes also called as chemical equivalent weight, and it is nothing but a ratio of a gram atomic weight, that is A weight. Don't confuse with the current and this A weight. That is A weight stands for gram atomic weight divided by valency, which means that we can easily write down material removal rate is directly proportional to a gram atomic weight. It is directly proportional to gram atomic weight, and it is inversely proportional to Z valency. Now, number of students ask me a simple doubt here. Sir, how the hell you can say that, sir? Material removal rate is directly proportional to gram atomic weight and it is inversely proportional to the valency. You explain. And this is what exactly question comes in the picture. Material removal rate is what? Directly proportional to gram atomic weight and inversely proportional to valency. Now, what is meant by gram atomic weight, right? And what is meant by valency? Now, let's understand the definition of gram atomic weight, and in simple term, we'll discuss about it. The amount of an atomic substance whose weight in gram is numerically equal to the atomic weight of that substance. Now, we know that whenever you take any object or any material, can I say it is consisted by some crystal structure, FCC, BCC, and so on. And whenever we talk about structure is nothing but this is the BCC, body-centered cubic structure, which means that at the corner of the cube, one atom is there, and at the center is also one atom. And these atoms are connected to each other by certain bond, right? Fine. Now, this atom is having certain structure. It has nucleus, it has protons, neutrons, and surrounded to energy orbit, it has number of electrons, right? Structure is same. So now, it's very simple that if in a material, if the number of atoms are more, right, in a cubic pattern, if number of atoms are more, naturally the gram atomic weight will be more. Because when I say ions are depleting, so can I say atom, if this is Fe atom, if I say that, sir, in a simple term, if I say that in this particular simple term, what is it? If I say that, sir, this is what exactly atom is, right? Fine. This is what exactly my Fe atom is. Now what will happen? It will what? It will deplete or release 2 electrons from outer energy orbit. And once it is released 2 electrons from outer energy orbit, this atom is release himself as a Fe++ ions. So can I say that ions are releasing, which means that it is coming from the atoms. So if I want to have more material removal rate, that means there has to be more ions should be depleted, and that means it should have more number of atoms. So can I say that in the material, if there are more and more number of atoms are there, the gram atomic weight will be more and metal removal rate will be also naturally more. As simple as that. Which means that in any material, if the gram atomic weight is higher, chances of metal removal rate will be higher because it has more number of atoms in that particular material. Simple story. So therefore we can say that, sir, the gram atomic weight, if it is more of the material, we can say metal removal rate is directly proportional to gram atomic weight. Now, how it is inversely proportional to valency? We have discussed one definition of valency. It is nothing but the combining capacity of an atom is called valency, or nothing but the number of valence electron an atom has to gain or lose from the outer energy orbit. So how many number of electrons it can lose or it can gain from the outer energy orbit to become a electronically stable or the stable atom, so that it has to release some electrons or gain some electron. And yesterday we have discussed that as far as zinc is concerned, in this energy orbit, actually it should have more number of atoms, but it has only 2 atoms there. So it's better to release these particular 2 atoms, and whenever they are releasing 2 atoms, can I say that rest of the whatever this particular energy cells or that particular energy levels are there or energy orbits are there, these energy orbits will become stable. It will become what? Stable. So therefore, the zinc will be releasing 2 particular atoms. 2 atoms will be released. So valency of the zinc is 2. Is it true? Yes. So now I'll take one example here. Let's understand that how exactly dynamics works in the picture. Suppose I am selecting A material and I am selecting B material. Now, right, how exactly metal removal rate is inversely proportional to valency and how exactly logic will apply to understand things in a simplified manner. Right, fine. So let's take an example. Valency of A is exactly equal to 1 and valency of B is exactly equal to 3. Right, valency is 1 and valency is exactly equal to 3. Now, which means that can I say that A will release 1 atom, that is nothing but A, or one particular ion will be depleted, that is A plus, and 1 electron will release. Is it true? Yes. Valency is 1. That means how many number of atoms can be released or how many atoms can be accepted to, or sorry, how many electrons will be released or electrons can be accepted to be chemically stable. Right, fine. This is what exactly definition of this particular valency. How many number of electrons are released. So now valency is 1, that means A atom will release 1 electron and then A plus ions will get depleted. And this is also where exactly is going to happen here. Suppose this is A, so 1 electron will get released and A plus ion will be get released. Is it true? Yes, because valency is exactly equal to 1. What will happen in the case of B? The valency is 3. So therefore can I say that, sir, B will release a 1 ion, that will be how much? B plus Y plus plus, because valency is 3, that means it will release 3 electron. It will release what? A 3 electron will be get released. So when the 3 electrons are releasing, when what? A 3 electrons are releasing, 1 B plus plus ion, this is what 1 ion will get released. So now if you compare very cautiously here, sir, in the case of A, when 1 electron is released, 1 A plus ion is released. But in the case of B, when the 3 electrons are released, only 1 B plus plus ion is released. So can I say that if in a term of A, 3 electrons are released. How 3 electrons are released? Very simply. So here there is a 1 particular 1 electron is released and 1 A plus ion is released. From here also there is a 1 electron plus 1 A plus ion will get released. From here also there is 1 electron and 1 A plus ion is getting released. Is it accepted, everybody? Yes, which means that in the case of A, if 3 electrons are getting released, can I say that simultaneously 3 A plus ions are getting released. So now in both the cases, number of electrons are released the same, but in the same manner as A has a valency 1, it releases 3 ions, whereas B has a valency 3. So when it releases 3 electrons, it releases only 1 B plus ion or B plus plus ion. So you tell me that in which case the metal removal rate is more. So in the A case, metal removal rate is more as valence is less. So when the valence is less, metal removal rate is greater. When the valence is greater, metal removal rate will be less. So therefore, we can simply say that material removal rate is directly proportional to gram atomic weight and metal removal rate is inversely proportional to valency. Now both the formulas, Formula 1 and Formula 2, you club together, and here the numerical comes in the picture. What we do? Formula 1, what is it? So metal removal rate is directly proportional to the charge carried per second, that is current, that is I, and metal removal rate is directly proportional to electrochemical equivalent, that is A by Z. Excellently correct. So we can write answer here. If I combine both these things, I'll say that material removal rate is directly proportional to, what is that? A into I divided by A into I divided by what? Z. But now it is having a proportionality. Now convert that proportionality into equality by bringing one constant. And if I bring one constant, I'll say that material removal rate now will be exactly equal to, there is one constant comes in the picture which is called as A into I, and that constant is, everybody knows that, it is nothing but called as F. And F stands for what? Faraday's constant. F stands for my Faraday's constant. So I'll say that F stands for a Faraday's, F-A-R-A-D-A-Y, Faraday's constant. Is it true? Yes. And the value of Faraday's constant is 96,540 coulomb. 96,540 coulomb. And now number of numericals can be solved from this particular exam or this particular numerical or this particular formula. Everywhere there will be so many questions comes in the picture, and these particular questions will be solved by this simple formula. So what is A stands for? Remember here, A stands for a current. A stands for gram atomic weight, and gram atomic weight has to mention in gram. Is it true? Gram atomic weight has to mention in gram. I stands for current here. I stands for what? Current. Current has to mention in what? Ampere. Ampere. Is it true? Ampere. Z. Z is what? Valency. Valency is number. It has no unit. So therefore, we'll say this is nothing but called as valency. It has no unit. And F is Faraday's constant. It has to be mentioned in the what? The coulomb. That is 96,540 coulomb charge. 96,540 coulomb charge. So if I put here the gram atomic weight A in the gram, the current value in the ampere, F, that is Faraday's constant, 96,540 coulomb charge, and Z valency number, my material removal rate, answer will come in gram per second. What is the standard unit is coming? The standard unit is coming gram per second. So material removal rate coming here in gram per second. So sometimes question comes simply in a GATE examination, calculate material removal rate in an ECM process, and these values used to be given in the problem. Very simple, straightforward, one question already asked in number of GATE examination. What is that? Gram atomic weight is given to you in the gram, but repeat myself, it should be in a gram. I, that is current density, should be given in the ampere. It should put in the ampere. F, Faraday's constant, it is a constant, 96,540 coulomb charge, and then Z is a valency, it is just a number. It does not require any unit. Okay? Valency of ferrous is nothing but 2. You put it 2 here. So AI divided by FZ is a material removal rate. Now this formula will take it and solve number of numericals. And don't underestimate this formula. It is very, very important. If I talk about ECM, this is the only formula you have to remember. Right, fine. Now, sir, there are number of influencing factors we have discussed. What are those number of influencing factors? One is nothing but, sir, material removal rate is directly proportional to amount of charge carried per second, which is current. Material removal rate is directly proportional to electrochemical equivalent, that is nothing but directly proportional to gram atomic weight and inversely proportional to valency. Now, apart from that, while solving the numerical, there are two more parameters are there where material removal rate is influenced, or material removal rate is influenced by these two factors. But we know that each and everything in the universe cannot be tabulated into the mathematical model. That cannot be converted into maths. That cannot be utilized to calculate numbers. And that's why this is the ultimate formula that we have. But apart from that, also there are certain factors who influences my material removal rate. Now, what are those factors? Next factor is the conductivity of conducting electrolytic solution. Now, I'll say that, sir, what does mean by conductivity of conducting electrolytic solution? Because you told us only that whichever the solution that we have selected, that solution should be conductor of electricity. And now you're talking about conductivity. So there can be chances that I am selecting this particular solution. Okay, fine. There is no problem. But conductivity can be different. If I select extremely high, good conductivity, right? If the conductivity of conducting electrolytic solution is very high, then what will be your material removal rate? And there might be chances that if I select this electrolyte, but if the conductivity of that conducting electrolytic solution is less, if the conductivity is less, then what will happen? So let's take a first example that if the conductivity of this conducting electrolytic solution is very, very less, then what will happen? So if the conductivity is less, then can I say that whenever the current has to pass through this gap present between tool and the workpiece, because there is a tool, there is a workpiece, there is a workpiece, there is a tool, and between that there is gap present. and that gap is filled with the conducting electrolytic solution. And now whatever solution is there, conductivity of that solution is less. So if the conductivity is less, that means whenever the current is flowing, can I say there is a lot of resistance created to the flow of the current between these two workpiece and the electrode, or workpiece and this particular electrode. So whenever there is a lot of resistance created to the flow of current, can I say the time required to complete electrical circuit will be more? Because the resistance created to a flow of current is very high, and we know that lot of energy of that electricity will get wasted only in completing the electrical circuit, because lot of resistance is created. Because we know that when there is a resistance created, energy will convert into heat, and therefore the energy that we want to use for depletement or dissolution of ion might be utilized somewhere else, and it is nothing but loss of that particular energy in the system, which might not be getting utilized for a proper cause. So which means that, so if the conductivity is less, there is a lot of resistance created to flow of current between workpiece and electrode. To complete electrical circuit, time required will be very high, and as resistance created to flow of current, the lot of energy will get wasted in the system itself, and energy utilized for dissolution of ions will be less, and therefore less number of ions will get depleted. And if less number of ions are depleted from the workpiece, my material removal rate will be fall down. So material removal rate will be less. Now you'll ask me a question, sir. It's very simple. These ions are depleting Fe++, and they are attracting towards that particular the tool. Here, this is the electrocoating principle. We can go back here and we can take example. Sir, here we can talk about that. This is the chamber. The ions are depleting. So now ions are depleting. That means there must have been somebody who should have pulled these ions from this workpiece material. And who is that? That who is nothing but electromotive force created by the tool. Because of the potential created, the tool which is negatively charged, it will just generate electromotive force, and because of that force, this workpiece will get depleted with the ions. So ions will get depleted because of that electromotive force. Now if the conductivity of conducting electrolytic solution is less, that electromotive force will be also less, and therefore because of less electromotive force, less ions will get depleted, and naturally my material removal rate will be less. Now in the second term, if the conductivity of conducting electrolytic solution is very high, now you tell me what will happen. If the conductivity is very high, naturally the quickly electrical circuit will get completed. The time required for flowing the current through the gap present between tool and the workpiece will be less. So time required to complete electrical circuit will be also less. As the time required is less, and there is extremely high conductivity is there as far as electrical conductor conducting solution is. So can I say that the energy required for traveling through that conducting solution will be less. So more energy will be generated or utilized to generate electromotive force, and because of that force, more and more ions will get depleted from the workpiece. So naturally, number of ions depleted because of more electromotive force will be what leads to more material removal. Natural statement, and therefore I'll say that material removal rate will be higher. Material removal rate will be what? Higher. So can I say that my material removal rate is directly proportional to conductivity of conducting electrolytic solution. If my solution is more and more conducting of electricity, then material removal rate will be greater. If my material removal or conducting solution has a less conductivity, then I'll say that material removal rate will be less. Now there was one question asked in engineering services. Let's focus on here. I'll ask a simple story here and you have to answer me. Sir, in the conventional machining operation, if the material removal rate is greater, listen carefully, most of the students fail to understand, but it's very simple, you will understand, no worries. I'm talking about material removal rate, right? Fine. If the material removal rate is very higher, material removal rate kya hai? Material removal rate is very higher, right? Fine. So when the material removal rate can be higher, when my depth of cut will be higher. Naturally, if the depth of cut is higher, material removal rate is higher, D stands for depth of cut here. Okay, very fine, I'm understanding. Now if the material removal rate is higher, what will happen to the quality of surface? You tell me that. Quality of surface means what? What is the surface quality which is going to get manufactured during machining operation if material removal rate is higher? Sir, if material removal rate is higher, which means that depth of cut is higher. If material removal rate is higher, depth of cut is higher, the size of the chip is coming out will be higher. For more size of the chip, forces will be higher. If the forces are higher, reaction force will be higher, vibrations will be more, which means that the quality of surface produced will be deteriorated quality, or rough surface will get produced. What it will produce? It will produce deteriorated quality, or it will produce my rough surface. It will produce what? Rough surface. I think so. Everybody understand the analogy, what exactly I am speaking here. So let's say that if my rough surface is produced when the material removal rate is higher, And that is what the reason that in a grinding operation, can I say grinding is finishing operation? Yes, sir. The abrasive particles are rubbing on the workpiece, and the particles, when they're rubbing, they generate microscopic scratches, and because of that, the material removal takes place, but it removal takes place in the form of powdery particle. And if it is generated a powdery particle and removal is happening in a very, very small manner and dust-like particle, what quality of surface it produces? It produces excellent quality of surface, which means that when my material removal rate is very less, if the material removal rate is very less, can I say that excellent quality of surface excellent surface finish will be generated. Do you understand that? Yes. Now you come back here, and here the engineering service problem we are talking about. Now we discuss about material removal rate is directly proportional to conductivity of conducting electrolytic solution. If the conductivity is higher, material removal rate will be greater. If the material removal rate is greater, can I say quality of surface produced will be poor. If the conductivity of conducting electrolytic solution is less, MRR will be less. If the MRR is less, can I say that excellent quality of surface can get produced. And therefore, excellent quality of surface finish, if you want to manufacture, can I say that conductivity of conducting electrolytic solution should be kept as low. And this was asked in a GATE examination. Now there is one statement also used. Whenever the conductivity of conducting electrolytic solution is very high, such a solution is called as passivating solution. Such solutions are called as what? Passivating solution. It is called as passivating solution. I hope so you are understanding the statement what exactly I am speaking. It is called as what? A passivating solution. Passivating, right? Fine. So passivating solution means what? It has very high electrical conductivity. If the very high electrical conductivity, MRR will be higher. What will be higher? MRR will be higher. If the MRR will be higher, can I say it leads to rough surface? It leads to what? Rough surface. That means, can I say that a reverse statement? To manufacture a rough surface, passivating electrolytic solution is used. And passivating electrolytic solution means it has high electrical conductivity. In the reverse direction, I can say that when the conductivity of conducting electrolytic solution is less, it is called as non-passivating electrolytic solution. Non-passivating electrolytic solution. And if the non-passivating electrolytic solution is there, which means that my material removal rate will be what? Less. My material removal rate will be what? Less. If my material removal rate is less, can I say that quality of surface finish produced will be excellent quality of surface finish is going to get produced. Excellent quality of surface finish is going to get produced at that particular point. So therefore, for excellent quality of surface finish or smooth surface finish, non-passivating electrolytic solution is used, whereas for generating rough surface, passivating electrolytic solution is used. And this question was asked in GATE examination. Right? So I'll say that for excellent quality of surface finish, which of the electrolytic solution is used? And answer is non-passivating electrolytic solution. And we have already discussed that my material removal rate is directly proportional to conductivity of a conducting electrolytic solution. But this parameter cannot be considered for mathematical calculation, right? So because of the limitation, we can't be considered this, but this is also a parameter which has impact on a material removal rate. Well, there is one more impact is there, and that impact is nothing but related to distance between tool and the workpiece. Distance between what? Tool and the workpiece. Now let's say that, sir, whenever the distance between tool and the workpiece is very small, and whenever the distance between tool and the workpiece is very large, it also has impact on MRR. So you take one example that suppose, hypothetically, one particular workpiece, that is one also electrode, that is positively charged, is kept as one corner of the room, and the second electrode is kept other corner of the room. You can assume that there is a large distance is maintained. If there is a large distance is maintained, that means to complete the electrical circuit, right? What exactly I am speaking, right? I hope so you are understanding the statements what exactly I speak. This tool is kept at one corner, my workpiece is kept as other corner, so gap between them is very large. So whenever I'm generating the potential, can I say that to generate more potential, so whenever I'm giving the power supply, can I say that as the distance between tool and the workpiece is very large, my current has to flow very, very large distance to complete the electrical circuit? To complete the electrical circuit, very first statement. And if the current has to flow large distance, which means that time required to complete electrical circuit will be also very high, and therefore material removal rate will fall naturally. And the electromotive force generated between tool and the workpiece, as gap is very large, will be also less. As simple as that. And if gap is large, electromotive force will be also very small, and therefore the rate of depleting of the ions will be falling, because electromotive force which is pulling these ions will be also falling, and therefore my material removal rate will fall. Opposite that, you assume that my tool and the workpiece is kept very near to each other. If my tool and workpiece is kept very near to each other, that means there is very less gap. If the gap is less, so current has to travel very small distance, so time required to complete circuit will be less. And the electromotive force generated by the tool on the workpiece material will be very high, and quickly it will attract, and it will deplete number of ions because of that high electromotive force. And as number of ions depleting are increasing, my material removal rate will increase. So very simple statement is that material removal rate will depends on distance between tool and the workpiece. If the tool and the workpiece is smaller, or distance between tool and workpiece is less, then more material removal rate can be achieved. And based on that, there is one application is coming. So here, let's take an example that in this particular place, we have selected plain particular workpiece, we have selected plain tool. Which means that if I consider each and every point of this particular tool, can I say that it is equidistant from the relevant point of my tool material? Do you understand that? Yes. So can I say that, sir, this is what exactly the average distance between a tool and the workpiece. Is it true? Yes. And can I say that each and every respective points are equidistant from this particular tool? Each and every the relevant point of the workpiece is at equidistance from the tool, and therefore electromotive force generated is same everywhere. So ions which are depleting from the entire surface will be same. Right, fine. Now I am changing the dynamics of machining operation, and understand that what exactly dynamics I have changed. I did one thing that here, right, I am selecting my tool here. This is what exactly tool. My workpiece is flat, like a metallic plate. You can assume that this phone is a metallic plate, right, fine. The top surface is flat. This is a 3D. This is what exactly actual workpiece is there. But in the reality, I'm taking this particular slide, I'm taking cross-sectional view so we can understand. So this top surface of workpiece is a flat. But I'm selecting my tool. Tool is not a flat. It has certain particular shape. Predetermined shape is created. So this is a convex shape. This is a triangle kind of shape is there, right? And we know that in reality, my this particular tool will be having one more dimension like this. So now you can understand very easily how exactly my tool would be. Is it true, everybody? I think so you are visualizing this, what exactly I am speaking. समझ में आ रहा है everybody? What exactly I am doing? Is it true? Yes. Said? Yes. Rav, is it true, everybody? Yes. So now you tell me that what happens. Sir, if I talk about this point, can I say that this point of the tool is very close to workpiece? Is it true? Yes. As compared to say this point of the tool is far away from the workpiece. Is it true? Same thing is applicable over here. This point of the tool is very close to the workpiece. And here, this point of the tool is somewhere in between. Is it true? Yes. So whichever the point of the tool, is very, very close to workpiece, can I say that from that point to the workpiece, extremely high amount of electromotive force must have been generated as compared to the point which is far away from the workpiece. And therefore, whichever point of the tool which is very closer to the workpiece, from that point, it will generate extremely high amount of electromotive force on that respective point of the workpiece, and therefore, rate of dissolution of ions, that is rate of ion depleting, will be extremely high at that particular point. And therefore, we can easily say that what will happen here, it can be easily understood here. That is nothing but if I say that, sir, this portion of the tool is very near. So from here, rate of dissolution of ions will be extremely higher. From here also, rate of dissolution of the ions will be extremely very, very higher. Now, when the ions are depleting here, that means the material removal takes place from the workpiece. So therefore, can I say that there will be shallow spherical depression will start creating, because ions are depleting, material removal is taking place, and as the material removal is taking place, ions are depleting. Can I say that the gap between tool and the workpiece will keep on increasing now? Now, initially, this was the gap. Here, if we consider at this location, what is the gap? This is what exactly gap. But because material removal has takes place from this surface, can I say that my gap has increased like this? If the gap has increased like this, what will happen to MRR? Just now we have discussed, when the gap is increasing, electromotive force will reduce, material removal rate will reduce. But to maintain the constant material removal rate, can I say gap between tool and the workpiece should be maintained same, and therefore, can I say that during the machining operation, there is a need that my workpiece should be feeded into downward direction to maintain the same gap, so that material removal rate will also remain same. And therefore, as soon as material removal takes place from the workpiece, gap starts increasing between tool and the workpiece. Therefore, tool should be feeded in a downward direction. So, tool should be feeded. That means tool should come closer, closer and closer to the workpiece material. So, therefore, what will happen here? Now, you need to understand that whatever the shape of this particular tool that we have generated, what is the shape of the tool and what exactly the shape is? Can I say that slowly, slowly in the same manner, material removal takes place from this particular workpiece, slowly, slowly, slowly. Now tool keep on moving in downward direction. And can I say after a certain point, can I say that replica of the tool will be generated onto workpiece material. A replica of the tool will be generated onto workpiece material. That means, can I say that if I'm interested to generate complex curvature, contour shape, convex shape, concave shape, this is the process comes extremely handy. Because in the conventional machining operation, we talked and we have discussed that, sir, complex contour shapes are very, very difficult to machine in the conventional machining operation, and that limitation is eliminated by electrochemical machining operation. So electrochemical machining operation is extremely famous to generate a complex curvature component. How? It is in front of you, because material removal rate is directly proportional to, or material removal rate is inversely proportional to distance between. If material removal rate is less, then the distance is less, material removal rate is higher. If distance is greater, material removal rate will be less. So that means MRR is inversely proportional to distance between tool and the workpiece. So this is nothing but called as 4 influencing factors of my MRR. Is it understood, everybody? Yes. Now we'll talk about numerical concepts, right? Fine. Now there is a little bit of theories there, but we'll not understand or go through that application advantage limitations. Most important thing is numerical, right? First is nothing but called as, sir, tell me mass material removal rate. Directly question comes in GATE examination, which is nothing but that tell me and calculate mass MRR, mass material removal rate. Is it accepted, everybody? Yes. So whenever I say that mass stands for what? Mass is measured in a gram, kilogram. Is it true? Yes. And we know that, sir, mass material removal rate has a direct formula, that is mass material removal rate. Mass material removal rate is nothing but, sir, A into I divided by what? Z into F. We know that A is gram atomic weight, should be in the gram. I is nothing but the current, should be in the ampere. Z is nothing but Z is nothing but a valency, that is a number, and F stands for a Faraday's constant. So if I put all these values in proper unit, my unit is coming gram per second, because we are talking about a rate. A rate has to be always measured with respect to time, and time is always second in a standard unit. So therefore mass material removal rate is exactly equal to A into I divided by Z into F. Now in GATE examination, what tricks they use, do you know that? They don't mention that calculate mass MRR. The simplest statement is written that calculate material removal rate, in the bracket unit is given gram per second. Now it's your duty, you need to understand that the gram per second whenever I say, that means I have to calculate mass material removal rate in a simple term. Now sir, the next question is coming in the picture. Don't calculate mass material removal rate. I'm not interested into calculating how much grams of material removal takes place, but I'm interested to calculate a volumetric MRR. Now what is meant by volumetric MRR here? Volumetric MRR means very simple, that instead of calculating how much is a gram of material removal takes place, you tell me that how much volume stands for what? Millimeter cube, centimeter cube, right? This is the way by which volumetric MRR can be calculated, which means that I'm interested to calculate what? Volume. How much volume of material removal takes place with respect to time. With respect to what? Time. So therefore either it can be what? Either it can be what? mm cube per second, or it can be centimeter cube per second, or it can be meter cube per second. So that we are interested to calculate. And mass material removal rate already we have calculated. Sir, you must understand, if I calculate or ask you a question, what is the definition of density, row density of material? Sir, it is nothing but mass of the material divided by volume. Divided by what? Yes, very correct, Bhave. So divided by what? Volume. Is it understood, everybody? Yes. Now, what is the unit of mass? Sir, mass is in a gram. What is unit of volume? Sir, volume will be in millimeter cube. Is it true? Yes. Now, rho stands for density. So what is unit of density? Standard unit of density is gram per mm cube. Standard unit of density is gram per millimeter cube. Now sir, you tell me that, sir, I am interested to calculate volumetric MRR. Mass material removal rate already आपके सामने है, and we are interested to calculate volumetric MRR. Mass material removal rate is given to you. So from this formula, can I say that volume is exactly equal to, volume is exactly, take a density to the right hand side, it will come to the denominator. So I'll say that it will be mass divided by rho density. Mass divided by what? Rho density. Is it understood? Yes, which means that whichever the mass material removal rate formula is there, you divide that entire formula by rho density, and then you'll get volumetric MRR. Then you'll get what? Volumetric MRR. So we can write down here volumetric material removal rate is exactly equal to the mass material removal rate, that is A into I, that formula will remain same, divided by A into I divided by Z into F, and it should be divided by rho, and it should be considered as a density. But point to be understand that whenever answer is coming here, that is what volumetric MRR, unit should be mm cube, right? Mm cube per second. And to calculate this answer in mm cube per second, please understand that rho density, density should always put in a formula. In what standard unit? And the standard unit is gram per mm cube. What is it? Gram per mm cube. Gram per mm cube. While solving the numerical, most of the times we have observed that the students don't put the formula or the value of density in a proper unit. Value of density in a proper unit. Students fails that, and therefore I'll say that they get negative answer or negative marks. So therefore I can easily understand here, these are the two formulas extremely important as far as GATE examination point of view is concerned. So what it stands for? Volumetric MRR is A into I divided by rho density into Z into F. Now, do I require to mug up these formulas? I don't at all require to mug up these formulas. Just remember that mass material removal rate. What is it? A into I divided by Z into F. Even that also I don't require to mug up, because I know that MRR is directly proportional to amount of charge carried per second, that is current, and it is directly proportional to electrochemical equivalent, which is exactly equal to gram atomic weight divided by valency. So there is one constant comes in the denominator, that is F, Faraday's constant. So ho gaya mera formula, that is A into I divided by Z into F. And now that mass material removal rate should be divided by my density. If I divide that by density, I'll get volumetric MRR. Now the question will not come in examination to calculate the material removal rate, mass material removal rate or volumetric. Most of the times question is coming in straightforward way, calculate MRR. Okay bhaiya, calculate karo. In the bracket, what is written? It is written like gram per second, or it is written like a mm cube per second. So from the unit you have to understand that whether we have to go for volumetric MRR or whether I should go for that particular mass material removal rate. I hope so you are understanding this, right? Fine. Now there is one more hint I'll give, that is nothing but, sir, whatever formula that we have discussed here, it is for pure solid. Now what is pure solid and alloy? Pure solid, pure copper. Pure copper stands for only copper metal is there. That is what called as pure. And if there is a pure material, that means for that pure copper, there is only one value of gram atomic weight and there is only one value of a valency. Right? Z valency. There is only one value for pure solid. But if it is alloy, if it is copper and aluminum is mixed together in certain percentage, 50% copper, 50% alloy or 50% aluminum. So can I say copper has its own density? Copper has its own valency? Aluminum has its own density and own valency. They both are having different value. So if the alloy is coming in the picture, and for the alloy if I ask you calculate mass material removal rate or calculate volumetric MRR, then what I'll do? Should I use this gram atomic weight of aluminum? Okay sir, aluminum thoda sahi lag raha hai, we'll take it. Is it like that? No. So this particular session, tomorrow there will be no theory. Tomorrow there will be only numerical concepts, and numericals will be solved in tomorrow's session. That is what exactly ECM ka entire previous year's GATE PYQs that will solve, and entire concept related to numerical. So if the alloy comes in the picture, how exactly we're going to solve that particular numerical? What is the formula? Because this formula is only applicable to pure solid. It is not applicable to alloy. I think so you are understanding what exactly I'm speaking over here. Right? So any doubt? Bhavya, Sudeep, everybody, whichever is watching this particular video. So you can comment, is there any doubt? I hope so you are understanding this beautiful session, what exactly we are discussing. Anyone there? Clear everybody? Yes. Sayed? Is it clear? Sachin? Sachin, Sayed, Shubdeep, Jeevan. ESC questions भी लेंगे कल. Don't worry. Vian Balaji. We'll talk about and take ESC questions also tomorrow. No worries. I hope so. Whatever fundamentals we have covered, you must have understood that fundamental. Is it clear, everybody? Each and everything in very systematic manner, in very straightforward way we have covered. Okay, then tomorrow we'll meet at the same time. Okay. Fine. So this is the time to wind up the session. And please do tell your friends that this is the only introduction. That's why I'm taking this topic in a very simplified manner. But when more interesting sessions will be coming, and that will be planned in next week or next to next week. In that session, we'll cover the entire production ka topic. If I take metal forming or metal cutting, then we'll cover entire fundamentals, and then we'll cover entire ESC and GATE questions. So you reach out to the rest of the students who are there, who will get benefited. Ask them to download this particular beautiful app, BYJU'S Exam Prep. Subscribe the channel, come down, interact with us, believe with us, and we'll walk together. I also, we are working extremely hard. We are passionate. We are loving all the students who are in the platform, and then we are working together for one common goal, GATE 2023. Or any examination you are preparing, whether it is a GATE or ESC or any examination of HPCL or anything is coming, we're always there to help you. Right? I'm dealing with the two subjects, production and industrial. Okay, fine. So till then, take care of yourself and happy learning. See you tomorrow.